want to thank Floris for being a special co-host here, and we're gonna rock and roll. Slideshow. All right, can you guys see my screen? All right, so this month that we're in of October is Moisture Management Month. So the plan for the year was to kind of talk about moisture management. Moisture management as a big topic is a very big topic in that all buildings need to survive, they need to shed water, they need to be there for a long time. So that first image of the hands on top of that house to protect it is kind of like what our goal is of the basics of a shelter. All right, so thank you to House Accelerator. My name is Kevin Brennan. I'm a passive house tradesperson. I also teach for the Air Barrier Association, and I'm proud to be a part of this community and share with everyone. All right, so everyone's got their game on. We're gonna just relax a little now. Listen to the ASMR of it raining outside. Nice and calm. Look at that building. It's in the woods. I didn't know that ads thing was going to pop up, but it does sometimes. And that building built 200 years ago out of logs and timber. What is it doing? Shedding water. It's heated. It's drying out. It's controlling vapor, controlling all the things we're going to talk about tonight. But I'm going to stop this because this goes on for 11 hours if you wanted to listen to this and relax to it. All right. All right, silly video. All right, so moisture management. When it rains, it pours, and the buildings we live in need to shed that water to keep the buildings operational. It also needs to keep them comfortable. If you've ever been caught out in a rainstorm, first thing that happens when you get wet, you get uncomfortable. As a fireman, when I get wet, it's not long until frostbite and everything comes in. So our houses need to be able to manage moisture. That's why we have roofs designed the way they do. Walls are vertical. Everything's governed by gravity and the physics of buildings. So what is moisture and how does it exist? It exists as a solid as ice. It exists as a liquid as water. And it exists as a gas. When it exists as a gas, it's in the vapor form, but it's also it could be existing as steam, which isn't very common in buildings, but it's also in the relative humidity of inside the air. So each molecule of air that's in the air has a certain amount of humidity into it. So the next kind of like basics of moisture management are moisture flows in 4 different ways. It flows with gravity, and that it goes down. It's governed by the weight of the moisture going down a wall, over a roof, shingle fashion. It also can act as it being sucked up against gravity through capillary action through certain materials such as concrete or brick, can wick through other materials that say some sort of fabrics or so. We also have moisture that moves through diffusion. That's the vapors going through the material, say the vapors going through a brick wall. And we have air transport, which to me is the big deal of kind of like managing moisture. So as we're talking about moisture, a lot of what I've learned in my career, I've had very great privilege of going to building science summer camp. In my first summer camp, I listened to Joe Lestibrick talk about why wood buildings rot. And he hit a moment with it where it was, aha. So when a tree falls in the forest, does it make a sound? I don't know, but it does. Does it make a sound? I'm not sure. But what happens when that tree falls, and why did the tree fall? The tree's dead. It hits the ground, and the ground is kind of moist because of the rain and the moisture and the dirt. And that tree is now being brought back into the fungal world. It's being eaten by slowly being wet for a long period of time. And that's slowly going to create topsoil with the leaves and the other branches, and it's going back to its organic state. So when something is wet for a long period of time, it's going to start degrading and falling apart. But if it's dry, it's going to last for a very long time. One of the great documents that helped me prepare for this presentation was the moisture control in new residential buildings. Joe has a way of describing information in the way he writes things that is just very methodical and could fill up the time. So this is a great piece of information for reference if you guys somebody wants to throw it in the chat, or when Floris is talking, I'll put the link in there. So my next mentor is my good friend, Terry Brennan. Terry Brennan, no relation. So blow a door guru. Everyone always asks, are you guys related? And we're not related, but he's a building science nerd. I'm a building science nerd. We've crossed paths on projects such as Cornell Tech and other things like that. But he was hired to do a guide called a moisture control, EPA guide to moisture control in buildings, construction, design, and maintenance. And it's a great technical document to understand how moisture is controlled and where it goes. So one of the key parts of that document is the red line test, the purple line test that you see here. So the first one on the right side is the blue test, right? So you would take a blue pen on a sectional drawing and you would draw out all in blue where the water is going to be managed. So at the fascia board and the drip edge over there, the moisture is going to drip off. When it hits the brick, it's going to hit the reservoir cladding of the brick, either absorbed or drip down. At the head of the window, it's going to hit the drip edge and it's going to flash off. It's going to shed water away. The roof itself is going to shed water on the top side of the roof membrane and then below the concrete. So you have all your lines and ducts adding up. If there are any gaps in those lines, that's where we need to clarify the detail, right? So everything's kind of shingle fashion. And then we go over to the left side, which is the purple line trace test in the document. And that's our air barrier. And the air barrier, a lot of people don't correlate with moisture management, but there's a certain amount of air that gets transported in the relative humidity of air that kind of can be perceived as a water leak in a building, or cause condensation, or cause such things as wood studs to rot, or plywood or sheetrock to get metal, to get moist and then deteriorate. So it's a great example. And this is that tenement of passive house kind of air tightness, that all the lines add up and that there are details for each one. And now systems. So the name of the presentation is systematic moisture management. And if you've heard me talk before, or ever, kind of like my religious kind of standpoint is find a system and stick with it. When I say stick with it, meaning just go with the entire manufacturer systems, or unless you have an oddball. So in my career, I've been lucky to be located close by 475, which distributes the ProClima product line. And it's from like the wall all the way up to the roof. You're able to install a watertight layer up the wall onto the roof and back down. Now that roofing system that you see up there is very European, and that it's a tile roof that we don't really do here in the US, but we are getting more and more popular in doing metal roofing and other more durable roofing systems. So it's about the system. So go with the system and stick with it. Where we run into trouble with buildings is condensation. Condensation happens on single pane windows, where we have our greatest experience with it, when it's high relative humidity and the glass gets cold and we can see our areas in there. A lot of times we talk about radiator placement. The building I'm in right now has big radiators underneath all the windows because we're throwing heat at the windows to avoid condensation. And what happens with condensation is that it's tricky in that it's in the air and we can't see it, we can't touch it. We can only measure it with certain specific devices to measure relative humidity. And when a molecule there is 86 degrees, it has large volume that the molecule can work in, and then it has 28% relative humidity there. If I then would reduce the temperature of that water air molecule, the relative humidity would increase. So it's the same molecule there, but I've now reduced it down. So the way I explain it in my training classes to contractors is that each one of those balloons that you see there have a certain amount of like blue ping pong balls in them that represent moisture or the relative humidity inside those balls. Then we have a molecule there at 70 degrees, 50% relative humidity that's on the inside, very happy, very stable. And then we hit a cold surface. When we hit the cold surface, now the temperature of that air reduces drastically and then condenses all the way down. And now that air is really saturated and we have it in the dew point. So very kind of like intuitive way to explain what happens inside the wall or at the glass. Now, at the glass, it's not so much of an issue in that it'll evaporate over time. But if that's happening closed inside your wall, you're going to have damage over time, no matter if it's a wood frame building or masonry building. An example of dew point. Dew point is something that can be measured, and it's relative to the relative humidity in the air, which is kind of important. So this is from Proclima's website, and at Proclima's website, it explains in this in this diagram that more moisture is transported through a 1 millimeter gap, which is just a butt of a sheetrock, into a wall assembly 1,600 more times than through the material. So you'll have more water damage that'll happen through gaps and cracks and imperfections in the air barrier than will go through the material itself. So airtightness is a great way to moisture proof your building. This is vapor pressure going from high pressure to low pressure. When we talk about materials, some materials are vapor open, some materials are vapor closed. And then the permeability of each material depends on the characteristics of it. And that vapor profile will change based on where you're located. So if you're down deep in the south, maybe your vapor barrier will have highly permeable and non-permeable exterior air barrier. Whereas here in the north, we may want to have a vapor permeable outside. So it all depends on what the design is. So another example of air barrier training that you can see here is I have a hot plate here. And this is one of the examples I wanted to do live, but didn't have the ability to do it because of my current situation of being at the firehouse. But this hot plate here is a hot plate. It's at 81 degrees Celsius, which is pretty hot. I'm just going to boil this water here. The one on the left with the white membrane is a vapor closed peelant stick that has a glass disc on the top. And there is no vapor going through that material. The one on the right is a vapor open peel and stick from Suprema, and you can see that little bit of condensation on the opposite side of that glass. And that's showing in real life that vapor is going through that material. Now, our buildings don't handle hot water in the steam form very often, but that's kind of visual dramatization of what's actually happening through our building assemblies and materials. So the systematic approach to airtightness is that we are looking at a system, an air barrier system, but it's also a WRB or a vapor control, air vapor barrier. So this is by Polyguard. This is from one of the trainings that we did with the Air Barrier Association. So at the base sill there is flashing. Everything's done in shingle fashion in that it starts at the bottom and works its way up. There are pretty much no reverse laps, and then the water will shed around. The penetrations are detailed with liquid flashing or peel and stick. This is a vapor closed system, but it's a full system of an air barrier, which is acting as the water drainage layer as well in the wall system. This is a Tremco system. The Tremco system is a butyl-based vapor closed system. That's with the letters on it. And it's a systematic approach towards making the building, or in this case, the mock-up, air and vapor and water tight. We now have also on this slide, the gray membrane is a fluid applied, and that fluid applied is vapor open. So vapors can go through that fluid applied. Then here we have a 3M product. The 3M product on the right side with the clear is it's a peel and stick product that's vapor closed. It's an air vapor barrier. The rough openings are all detailed with their flashing membranes. The base detail, the inside corner, they're all done with their flashing membranes. And then the white membrane on the outside is it's a vapor permeable peel and stick product. So it's kind of like an STP applied onto a sheet membrane, and then it's put on the wall. So it acts like a peel and stick, but it's really like a fluid applied STP, which is being very common in the industry as a vapor permeable product. So these are the systems of many different manufacturers that do air barrier and WRBs as a part of their systems. Then we go back to Proclima, right? So Proclima's system, if you look at all the detail components, so one of the reasons I love to use the European kind of based air barrier systems is that you have all the tools and the tricks to make the building airtight, which will also make it more resilient and less susceptible to moisture in the end. So we have a peel and stick on the outside, the Hero, the Mento 3000 on the roof, all the tapes that are sealing every single joint that's going across, and then the auxiliary components, the Roflexes, the gaskets, all the other tricks that you may need to seal the system. Another systematic diagram from the Proclima system shows you all the components and how they work. So the Proclima system that you're looking at here is the intelligent membrane on the inside is the vapor control layer, and that vapor control layer stops the air on the inside where the air is warm, and then it'll allow the vapor to go through if the moisture in the cavity gets too high. So that's where it's Intello, it's an intelligent membrane. And the story that I always remember is that the intelligent nature of it, I believe, comes from the baking industry. Whereas you take a piece of bread and you put it into a bag, a paper bag, the vapor goes through, and over time it'll rapidly, get stale. Whereas if there were just a little bit of a vapor control plastic in there, it'll actually control the amount of humidity inside that bag where you're storing the bread and allow it to come out. And that's what they use within this system. A lot smarter and more science goes into it than just baking bread, but nobody likes stale bread or too moist bread. So this is an example of a house in the Pacific Northwest that's using the Proclima system to manage moisture. The Mento is on the outside, detailed out for the windows. It's got a metal roof, which is shedding the water from the outside. The Mento is a sarking membrane, a 3-layer TEF membrane that's fastened onto the building mechanically. It's a great product and system. And these are the components. So this is a little bit of the components from my work that make that airtight layer possible: the tapes, the membranes, the gaskets, and working clean and smart using primer and all the tricks and tools to make the building airtight, which airtight from the inside, watertight from the outside. A project I worked on that on the upper left on my screen is an older building. They did a renovation on the top 2 floors, the attic and the second floor. And then the next renovation was the bottom floor and the basement. So the upstairs was done, and then we insulated the outside with some wood fiber board. We coated the outside on the upper right with Mento, detailed out all the windows, and then they put on a rain screen system of the cladding, which is this, I believe it's a wood, I don't know if it's fiber cement or it might actually be cedar, but it's a fully drained rain screen system. This project's in Brooklyn, and it's a beautiful project. It did very, very well. And you can tell by the old architecture, the deep overhangs, that it's designed into it to shed the building from water. But the greatest risk in this building was interior moisture accumulating and getting stuck or trapped inside that wall, or rotting out the deck that would be attached to this building in the future. Now, on the other side of our work, the interior vapor control layer, we have another vapor intelligent membrane by another manufacturer, Partel, and that membrane will protect the inside from being exposed to warm air hitting the cold surface of this masonry structure. So if the moisture gets trapped in the wall and then hits the cold surface, it'll condense. And this is the systematic approach towards it. So the window bucks, the plywood, then get taped. You can put in, and then we blow dense packed cellulose in there. The black membrane that you see painted on the wall is their first version of their fluid applied air barrier. We used it in the rough opening. We used it on the party walls. It's airtight, the building, and went across. All right, how am I doing on time here? I'm flying by, right, guys? All right. So in these masonry retrofits, I have the first project I worked on was 88th Street. And we had a real world experience with this building, in that the top bulkhead had an exterior peel and stick membrane on the outside. So peel and stick, beautiful, asphalt-based, non-permeable. Vapor doesn't go through it. And then we came across this little electrical BX penetration that goes through there. That BX penetration got torn and put around. So I had to make the repair. When I made the repair, I was like, let me seal this on the inside and the outside. So I opened up the inside, and when I opened it up, I'm taking out the cellulose. And as I'm taking out the cellulose, there's only about 2 inches of cellulose there. I start to get to the outer edge of where the exterior of that wall is, and I could feel that it was wet and it was saturated. Like it felt different. Cellulose is normally dry, but for that last half inch, it was saturated. And it was that aha moment for me in that the air transport of hot, moist air coming in contact with that cold surface of that outside, then hit its dew point, and then condensated and then stuck within the first inch of that cellulose that was fully saturated, and you can almost feel the moisture in it. But the rest of the other inch and a half was dry. So the cellulose had the ability to absorb the moisture and wick it through to the outside. The Intello, as the moisture increased, it allowed it out so that it had the ability to dry out, wasn't trapped in that wall. So that's my real world experience with moisture as transport for that building. So the conclusion of the presentation is we need to look at buildings as a system, right? Stick with the system and go with it. Managing moisture starts from the bottom and works our way up in shingle fashions. And that the kind of like lesson that I'd really like to hit home really hard is that airtightness is just as much about shedding water and preserving of a building as shingle fashion and moisture on the outside. In construction, we're all feared of leaky windows and doors, but the airtightness and the moisture transport in a building can just be as risky in the rest of the product. So air barrier components require installed that they're drained. You'll need to address mechanical systems with airtight buildings. Understand how materials perform in an assembly subjected to different environments. The big kind of like debate in our culture is that North America is a really big place, and that there are climate zones are very different. So depending on where you are in that heating degree zone map, you may be really, really cold and have risk of condensation. You may be a moderate climate. You may be in the South where you have no heating degree days or very limited heating degree days, and your air barriers and systems. So you have to actually manage them and know where they are. Happy to answer them, but it gets very confusing based on geography. So yeah, I'll open up a wormhole there. So last one is building enclosures are important to performance and efficiency. So I'm Kevin Brennan. I am, that's my presentation. That's what I'm sticking to. I'm very lucky that my co-host or guest speaker here, Floris, is going to help us nerd out with his presentation, and then we'll be able to answer anyone's questions about moisture management or so. But thank you, everyone.
So yeah, we're going to look a little bit further, as Kevin had indicated. Air control is pretty essential. We like to do that on the inside to keep that humid air from getting into our fibrous insulation. And as we've been saying, if you can't keep the building dry or can't keep yourself dry from the outside, we're cold, we're uncomfortable, and the building will very likely fall apart. So, but we need to keep it also well built from the interior perspective. So there's what we're going to look at here is
the lead thing. Is it starting?
That the airtight is very important on the inside. For one, in the air quality, we don't want air wafting in and out. For comfort, if the drafts are uncomfortable, for durability, and of course for energy consumption. So why is this not advancing? This is, here we go. So the biggest tool we have in our toolkit is the blower door. The blower door doesn't lie. The blower door doesn't scream at you. The blower door doesn't get angry. The blower doors will just show to everybody on the job site where the leaks are and what needs to be fixed. And once we do a good job, construction workers actually understand this. If the second blower door, nobody's upset or offended. There's no super or architect or site manager that's screaming at them. We just have to find the leaks. So it's a very essential tool that we like a lot, because it will allow us to make our buildings very airtight, which will mean that they will perform as intended, and that the energy model actually will work, because we know we keep the conditioned air where it should be, which is inside the building. The second part of that is then, so now we have a good airtight layer. Now we have to assess our wall assembly. So Kevin talked about the dew point, which is a very simple rudimentary tool to assess if the dew point is in or out of the wall, but it's not very sophisticated. You can also use the glacier method, but it's a one-time snapshot, which has a couple of problems. It doesn't consider heat or moisture storage in the insulation. Wet insulation doesn't work. So if you have wet insulation, guess what? the glacier method doesn't, the graphs change. So it doesn't do this redistribution of liquid inside the insulation. And there's also no coupling of heat and moisture transfer in this dew-point glacier methods calculation. So it's not very helpful to predict if our buildings will stay dry. How can we assess this more accurately? That's with the Wolfie Pro model. So this is actually a computer model that does an hourly calculation and takes into consideration how the moisture and the insulation values and the vapor permeance of the materials change over time in these assemblies, over time based on what they experience, what happens with relative humidity, with the moisture, with the temperature. So, and with the solar radiation on the building. So it takes a lot of things in consideration. You will actually use the processing power of your computer in the right way. The computer actually uses this ridiculously high-powered input, processor that these computers now have. When I started doing this about 12 years ago, it would take a little while to get the Wolfie calculated. Now with the new computers, it goes a little faster, which is kind of nice. So we normally run 5 to 10 year analysis and see if these walls or roofs work well. And then we can see, do they stay below 15% moisture content? So they're safe, low risk. Below 18%, well, which is still okay for wood, but not for OSB. Plywood, maybe. 20%, it's kind of the danger threshold for us. Definitely don't want to go above it. And way above 20% is risks. Mold, rot, structural decay is pretty likely. So we don't want to design to the 20%. We like to stay below the 15%. Why is that? Well, then we have safety factor. Then something can happen. We can have a little leak in the air barrier. Somebody might hang a lamp, pierce our air barrier. It's not the end of the world because we have some drying reserves that we have some safeties. So moisture-driven damages, condensation, wood rot, corrosion, interstitial mold, and the freeze-thaw cycle can all be affected by this interior air barrier not being perfect. This is something to consider. Why do we need this perfect or almost perfect interior air barrier? Well, otherwise, the glacier method or the Wolfie calculation, they do not work. If there's air wafting in and out, these analysis tools have no value because there's so much air driving so much moisture into the wall. We cannot count on these methodologies anymore. So the risk is much higher. So what are the inputs in our Wolfie calculations? So the indoor conditions, occupancy, the air tightness, and the ventilation rate. So how much fresh air do we bring in or not? The dew point or or versus dynamics. So the temperature, the relative humidity, the wind. Is it wind washing going on, and the rain? If the outside cladding wet or not. And then the assumed embedded moisture after construction. We do want to make sure that in construction, we don't have wood moisture inside of our assemblies, especially not in flat roofs, because that could take a long time to dry out. So then we do these hourly calculations, and a lot of things go on here. The solar radiation, convection, evaporation, enthalpy. So you can see this is a very complicated calculation. That's why the processor has to work so hard. How did they define this then in Wolfie? Well, they did a lot of field testing, both at ORNL in Charleston and in Germany. So they actually calculated and made models to see what happens, and then actually check this against the real world data. So now we have a tool that actually can reliably predict how our buildings will perform. We also have to consider that, materials are not static. Here, what I said, your insulation value will be highly dependent on your moisture content of your insulation. Here you can see that thermal conductivity in metric. You can see how it depends on the water content of this insulation. And you can see that your insulation value actually, once it reaches a certain moisture threshold, the insulation value drastically is reduced, which again, then your wall doesn't work anymore, and it actually gets colder and colder and colder, which might mean that it condenses more and more and more. So intelligent vapor retarders, as Kevin also said, maximum protection. You know, we keep the moisture out in winter, but can let the moisture dry inwards in the summer. 13 perms in the winter, 0.13 perms with it if there is moisture in the wall and it needs to be driven out. So very vapor and open. So how does this, if we do this? Well, there's the calculation of the heat transfer and of the moisture transfer. And this is coupled back and forth. So it actually checks itself. So there's actually 3 equations going on and making sure what happens with the moisture, but then also with this heat transport and with the insulation values. So over and over again, more than 8,000 times a year. Of course, there's some challenges here, and that's where we're going to look at. There are a couple of projects here. So roofs are often vapor barriers, especially American roofs with asphalt shingles or flat roofs. So we don't want to have 2 vapor barriers. Everybody's always taught this, I hope. So if you have a vapor barrier on the outside, you shouldn't have a vapor barrier on the inside, but you can have a smart vapor retardant on the inside. Otherwise, the moisture could get into a small leak, but it would never be able to find the way out to the same hole. It would just bounce in there forever and cause issues like this. This is a SIP roof. There was air leakage between the seams of the SIP. It condensed on the backside of the asphalt shingles. But now it tried to dry back, but it couldn't find the hole back, the way back through the hole it came into. And so now the OSB got wet and you got mold in this asphalt flat roof, asphalt shingle roof. So maximize your drying potential. So smart vapor retardants, you see here every cycle, every summer, winter, you can see it can dry out. But OSB sheets or polyethylene sheets, they don't have the same inward drying capability. So now we have a Woofy model. So how do we check these roofs? Well, we check them in Woofy, but we also do some real life checking. So how do we do this? We do this with 2 methods. One is the OmniSense module and router. This is this little sensor here on the left. You can install in your roofs in any assembly, and it actually checks the wood moisture content and relative humidity of your assembly. The router then is connected to the internet, and you can get these nice readouts where you can see what the moisture percentages are. So then we can see what's going on after 1 year, 2 years, 3 years, 4 years, or 5 years. Eventually, it should be very boring, and we know it's safe, and we can turn off this system. So here was a really great EcoCore project in Maine. Flat roof, 14 inches of cellulose, Intello on the inside, but the flat roof is vapor close on the outside. And here we have 4 or 5 years of moisture sensor. And you can see there was a little bit of construction moisture. Actually, in the first year, you see that big spike. But then you see over the 3 eventual seasons, this dries inward. So this was, of course, not a great way to start. That they had some construction moisture in this assembly, but you can see the safety that this Intello system brought. And also that it was validated, because we saw in Woofy that it should work, that this cellulose can dry out over those next 2 years. So that's fantastic and good to see, and also with the real life validation. Here we have Minneapolis Climate Zone 6, good air tightness, passive house, versus index of 8 by Tim Ian. Good energy house. Walls are kind of boring, no Woofy needed because it's vapor open on the outside, so you can dry outwards. The SIP sheeting as the air barrier on the inside. It's a little bit vapor retarding, but open enough, so boring, we don't have to Woofy it. But flat roof, so same thing. Intello on the inside, little bit of foam on the outside to make the taper. 16-inch truss with cellulose. So what do? Well, we do a Woofy, but we also monitor this roof. Very nice airtight details. You can see the Intello over the interior walls already pre-installed, so the air tightness is continuous, and the Intello inside the rooms can be installed later. So here we actually use a very simple method. We have 2 screws, 1 centimeter or ½ inch apart, and we use a moisture sensor, an exact moisture sensor or RH monitor, and we just connect it with a long wire in the completed roof. And here we can actually see for this first winter, it's all, it goes a little bit in January to 16% moisture content, probably a little bit of construction moisture coming out of the wood. And Tim is actually supposed to get me some more data so we continue this for 1 or 2 years to make sure that this roof is working as we think it will. Here's actually the last Vermont timber frame project from 2013, and very good air tightness, climate zone 6 again, timber frame with foam-free flat roof. We had to push this a little bit further because we were pushed very hard by the building inspector that he didn't believe this would work. So we put some monitor sensors in there, and he eventually gave the sign off with a PE that we convinced this was a good idea. It should work engineering wise. Again, the walls are very easy. Get dry inwards, get dry outwards, some DB plus on the inside. But the roof, we did the same thing. Didn't use the OmniSense, but used the wood moisture sensor. And here we show in Wolfie actually that over time it goes, it's a little bit high up at 20%. And actually here we compared a dark roof versus a light roof. And you can see the dark roof dries much, much faster. You see after the second winter, it's already below 16%. Well, the light roof, you can see how long it takes to burn out the construction moisture. Of course, ideally you don't have any construction moisture or very little. So you don't have to wait that long to get dry. But here we can see actually the Wolfie was very conservative with the construction moisture, and over the years it's below 10% moisture in this roof. So this is actually a very safe roof because they made sure they built it in a dry way. So that's my rapid fire 33 slides. I hope you enjoyed it, and let's go to the questions.